Last week, when solar observatories simultaneously sounded the alarm about an X9 class flare, I immediately knew this wasn't one of the sun's usual tantrums. It was the kind of event that could rewrite everything we think we understand about space physics. I've seen plenty of solar storm data before, but this time was different. A coronal mass ejection CME shot out at roughly 2,000 kilometers per second, carrying enough plasma and magnetic field to shred any small object that happened to be in the wrong place at the wrong time. NASA, NOAA, and ESA almost instantly reached the same conclusion, and I agreed with them, because based on everything we know, there is no scenario in which a loosely structured object like a comet could survive a direct hit like that. The plasma impact would disintegrate the structure starting from the outer layers, electromagnetic stripping would peel every molecule off the surface, and the thermal shock from the superheated plasma cloud would sever whatever bonds remained. The problem was, at the exact moment the CME left the sun, 3I/ATLS was sitting right in its path, a coincidence so bad that if I hadn't seen the data myself, I might have thought someone was staging a durability test. The initial prediction, anything but optimistic, was crystal clear. ATLS wouldn't last more than a few minutes once the CME swept over it. But what happened next is the part that made me stop, stare, and question every model we're using. When the CME engulfed the region, ATLS was traveling through every monitoring system from SOHO to Parker Solar Probe, lost track of it completely. No reflected signal, no ionized remnants, no trace whatsoever that ATLS had been destroyed or still existed. It didn't fade out. It didn't break into pieces. It just vanished as if erased from space for more than 30 minutes. I double-checked for interference, instrument error, even the possibility that data filtering software had mistakenly removed the signal, but none of that was the case. And then, as the plasma began to thin out and radiation dropped back to levels where sensors could function again, the first image that appeared made me frown the way. Only the impossible can 3I/ATLS reappeared, completely intact, to the point that if you put the before and after images side by side, you could barely tell the difference. No fragmentation, no loss of brightness, no smear or debris trail that should have been there if an X9 class CME had actually hit it. In that moment, I realized we had just encountered a cosmic scale exception, an exception big enough to force every model to be reconsidered from the ground up. This ancient interstellar object, by everything physics has ever taught us, should have been turned to dust, but it wasn't. And that's when I knew every model, every assumption, every familiar theory no longer held up. When Atlas reappeared after the solar storm, unscathed as if it had just walked out of an impossible test, I had to rewind everything we knew about it, because if we want to understand why it survived, we have to go back to the moment it was first discovered. Atlas was identified in mid-2025, initially just a faint streak, barely distinguishable against the star field. At the time, no one thought it would become the most controversial object since Oumuamua in 2017 and Borisov in 2019. But then its orbit was calculated for the first time, and that's when things started getting strange. Atlas's orbit was almost perfectly flat, aligned with the ecliptic plane to within a few degrees, something extremely rare for interstellar objects, since most of them come barreling into the solar system from random directions. The next oddity at speed, Atlas was moving faster than most solar system comets, yet with an unbelievable steadiness, no minor wobbles typically seen when an object interacts with the solar wind or collides with interplanetary dust. And then there was the brightness issue. Starting in September, Atlas began brightening in a way that didn't match any of the sublimation models we used to predict comet activity. Instead of gradually increasing with solar radiation intensity, it brightened in strange step jumps, as if inner layers of material were being revealed in stages. Yet even at peak activity, Atlas produced no dust tail, an anomaly that left many astronomers baffled. A strongly sublimating comet cannot fail to produce dust. That's a principle confirmed for centuries. But Atlas was different. It glowed, it outgassed, but it released no solid particles large enough to form a tail. In other words, it behaved like a comet that wasn't a comet. The first spectral analyses from ground and space-based data only lengthened the list of surprises. An unusually strong green spectrum, high CO4 content, and abundant C-THOS and NH-THOS compounds signaling chemical activity, very different from the Oort cloud comets we're familiar with. Then JWST weighed in. Deep infrared data and NER spectroscopy revealed what remains one of the biggest keys to explaining how Atlas survived the CME. Its outer shell had been bombarded by cosmic rays for billions of years, forming a radiation crust tens of meters thick. If you're a scientist, that discovery is already fascinating. But if you approach the problem like an engineer, as I do, you see something entirely different. Armor, natural armor, yet with exactly the properties you'd want if you were trying to protect an object from radiation, cosmic dust impacts, or extreme temperatures over a billions-year journey. And because of all that, the scientific community was already paying close attention to Plalis long before the solar flare. Its orbit wasn't normal, its speed wasn't normal, its brightness wasn't normal, its structure wasn't normal, its chemical composition wasn't normal, its outer shell wasn't normal. Each part on its own was already an anomaly. Put them all together in one object, and Atlalis became a huge question no model could fully answer. And when the solar flare happened, it only made that question many times more urgent. If you're an engineer, you can't look at Atlalis without seeing a very different kind of logic. Everything about it shouldn't happen, but it does. And because of that accumulating weirdness, by the time October rolled around, we started seeing a series of signs so strange that we had to treat Atlalis as a special case study even before the solar flare erupted. I clearly remember the first moment I saw the water outgassing rate data, 5.7 Castor 10 use molecules per second, a number that means almost nothing if you're not familiar with comet physics, but to anyone who really understands, that's an extreme outgassing level, 30, 40 times higher than just a month earlier. If a normal comet reached that rate, it would be spewing tons of water vapor along with dust, creating a tail millions of kilometers long. But Atlalis didn't. 3 coronagraphs, SOHO/Sol A shell, Stereo Core 2, and the coronagraph camera on GOES 19 all showed the same absurd thing. No dust, none at all. Just a faint, steady emission streak, a glow that carried no solid particles, meaning Atlalis was losing water at an extraordinary rate, but releasing zero solid matter. If you want a mental picture, imagine a boiling kettle with no visible steam, just heat, no water droplets. This wasn't just odd, it contradicted everything we know about comets. And then there was the brightness. Normally, a comet's brightness increases as a simple power law based on distance from the sun. Atlalis refused to follow that rule. From early October until right before the solar flare, its brightness doubled faster than the standard model. At first, we thought it was just fluctuation from uneven heating of the outer layers. But when we cross-checked data from Lunar Observatory, Catalina Sky Survey, Mount Lemmon, and many well-equipped amateur stations, everything pointed to the same conclusion. This wasn't error. This was a real trend. Atlalis was brightening in a pattern no one had ever seen. An object with intense activity, sudden brightness jumps, but no dust. That's not comet behavior. That's the behavior of an object with a surface too smooth fragment, or material unlike ordinary ice rock, or a surface too tough to break into particles. From an engineering perspective, you immediately see the issue. If Atlalis isn't producing dust, its mass isn't being lost as particles, only as water vapor and gas. That means its structure doesn't weaken when it becomes highly active, completely opposite to solar system comets, which are always visibly eroded when they approach the sun. By this point, Atlalis had become an object of more than usual attention. A team at the University of Arizona had even labeled it a priority monitoring object before anyone knew a solar flare was coming. From orbit to chemical composition to brightness to outgassing behavior, everything about it forced observers to ask questions. No one knew what it was, but it clearly wasn't behaving like anything we imagine an interstellar comet should. So when NOAA issued a warning about a major flare headed straight for Atlalis, more than a few of us wondered what happens when an object that is abnormal at its core faces one of the most violent events the solar system can produce. Still, no one expected the answer to lie completely outside every limit we could predict. The moment the X9 class CME slammed straight into the region where 3I/Atlalis was traveling was when I realized everything we thought we understood about how comets behave in extreme plasma environments was about to be tested to its breaking point. I've watched plenty of solar storms, but the data from Parker's solar probe this time had something different. Proton density spiked vertically, particle stream speed far exceeded what high-energy models predicted, and magnetic field distortion stretched into perfectly straight segments, the kind of signal you only see when the sun throws a plasma punch, powerful enough to turn a porous object into fine dust in an instant. I looked at the plots and didn't need anyone to explain. The moment a few values appeared, I knew what the conclusion would be. At this intensity, if Atlalis was still there a few minutes later, it would mean our entire modeling framework needed to be rewritten from scratch. When the CME reached Atlas's location, the first thing that happened wasn't a brightness surge from ionized material, nor an elongated image like comets torn apart. I stared at the screen and watched ALS disappear, not fade, not get yanked out of position, but disappear in a way that was absolute emptiness. Position data dropped straight to background noise. The brightness chart went flat as a calm lake. Ionization sensors found no tail fragments. Anyone seeing it for the first time would think the instruments had failed. But I've worked with space data long enough to know that 3 separate instruments losing the object at once isn't a malfunction. It's something happening outside what the instruments were designed to model. While Atlas was gone, Parker kept sending alerts that only made everything stranger. The algorithms estimating plasma density kept returning structural breakup expected, meaning the models predicted that anything with comet-like structure had to be disintegrating in that region. That made perfect sense. Superheated, superdense CME plus distorted magnetic fields would fracture material through propagating cracks, causing the core to split into tiny pieces. But the paradox was that Parker predicted breakup very clearly while the data showed zero evidence, no unusual ion spikes, no ejected material fragments at all. When models and data don't match, usually the data is wrong. This time the models looked like a confused person trying to force reality into familiar rules and failing. So H.O. provided the next piece of this bizarre picture. In the chronograph frames, exactly where Atlas should have been blown away by the CME, I saw a thin, curved glow, not the expanding bow shock wave we've observed hundreds of times when comets are destroyed by CMEs. This shock wave didn't expand in a bow shape, it contracted, bending in a curve around Atlas's position. I know that shape well. Plasma only bends like that when it encounters an object of high density or a surface so tough that the particle stream can't penetrate. That's not comet behavior. That's the behavior of a hard object. No one uses that term in astronomy, but when plasma slides around instead of punching through, I don't know what else to call it. LASCO C3 even captured something that made me lean closer to the screen, a faint dark region, a void in the plasma flow briefly visible for a few frames. Plasma voids only appear when something inside the particle stream casts a plasma shadow, meaning the object can affect the flow of charged particles. Only dense objects or objects with extremely hot surfaces do that. Comets can't. Ice certainly can't. The weirdest part was that while Soho showed some signs the object was still present, Parker continued to record zero debris, not a single dust grain, not one ionization spike, no evidence at all that the object was disintegrating the way models predicted. I looked at the data and thought, like an engineer, if the object isn't destroyed, but the models fail to predict breakup, is the problem with the models or with the assumption that this is a comet? The truth is, none of the models on the table at that moment could describe a porous object surviving an X9 plasma blast without leaving debris. We tried clinging to the simplest hypothesis. It must have broken up and the remnants are hidden by plasma, but Soho wouldn't let that hypothesis live. The next chronograph image came in clearer, and right where Atlas had been, a familiar point of light gradually reappeared in the thinning plasma. No distortion, no brightness loss, no positional shift, no sign of damage, not even minor. I checked the numbers, the images, then the numbers again. Everything matched. Atlas didn't just survive, it survived in a way that didn't fit any destruction model we have. In that moment, I understood we weren't just watching a strange object, we were witnessing an object that flatly rejected every prediction, as if it never cared about the plasma storm that had just swept over it. And the only question left, in the strictest technical sense, was what exactly is this thing made of that it treats an X9 class CME like a gentle breeze? The moment that familiar point of light gradually reappeared in the chronograph's field of view, I knew we were about to have to throw out an amount of theory so large it wouldn't be easy to accept. Atlas didn't come back as a faint remnant cloud or an eroded core. It came back exactly as it had been before the CME touched it, sharp, steady, and showing absolutely no sign of having endured a plasma collision powerful enough to destroy a comet in under 3 minutes. Its brightness was almost identical to the pre-CME value, no amplitude drop, no unusual fluctuations, no energy loss typical of an object that had just been stripped of its outer layers. I checked 3 times, cross-referencing data from Soho, Stereo, and even ground stations with indirect viewing angles. The results were so consistent, they left me both stunned and feeling personally challenged. ATLS hadn't weakened at all. No debris was detected anywhere in the region. The CME had just swept through. No tail fragments, no ionized dust layer, no enhanced OE emission, or any sign that thermal shock had cracked the surface. All that appeared was ATLS itself, intact to the point that if you didn't look at the timestamp on the image, you'd easily think it was a frame taken before the event, not after. The observatories couldn't hide their confusion. The most experienced researchers, people who had watched dozens of comets get erased from the map by CMEs in minutes, couldn't find a reasonable explanation. Some suggested we might have misunderstood ATLS's structure, that its durability was higher than ordinary comets, but the next question came immediately: how much higher? Durable enough to survive million-degree Kelvin plasma, an environment where rock, ice, dust, even light metals are continuously peeled away. That's no longer a normal difference. That's a gap big enough to change the entire definition. What struck me most wasn't that ATLS was still whole, but the way it returned, as if it had never left. No gradual fading then brightening, no reformation process. It simply snapped back into the frame like a device that had only temporarily lost signal. I'm not implying anything here, I'm speaking purely from an engineering perspective. Most natural objects under massive energy impact leave traces, but here the only trace was the complete absence of any trace. And in science, a data void can sometimes be scarier than anomalous data. The next thing we did was compare infrared brightness and chemical spectra before and after the CME. The result? Almost no change. ATLAS showed no signs of abnormal heating, no surface loss, no increase in outgassing. If you didn't know a CME had just happened, you'd think ATLAS was in a perfectly normal stable phase. This contradicts every observation experience we've ever had. A CME strong enough to simultaneously corrupt data from 3 observatories wasn't strong enough to leave even a scratch on ATLAS. No comet has ever done that. No model has ever simulated that. And no researcher on the live channels at that moment could accept the reality without feeling their own thinking shaken. I remember someone on the internal channel whispering, half joking, half serious, if this is a normal comet, the sun owes physics an apology. The line sounded funny, but it perfectly described what we were facing, a moment when ATLAS didn't just break predictions, it shattered faith in the stability of the models we've long treated as foundational. For me, that moment wasn't memorable just because ATLAS survived. It was memorable because of how it survived. No defense, no damage, no trace of a plasma impact that should have erased every porous structure in the solar system. This was no longer a single anomaly. This was defying all predictions, a wholesale rejection of what we thought was certain. Looking at ATLAS reappear intact, as if it had never passed through a gigantic plasma storm, I had to face the hardest question. If everything had gone the way physics says it should, what was supposed to happen? And the answer, setting all emotion aside, is very simple. ATLAS should have died, quickly, decisively, and with no way back. An X9 class CME is no joke. It is one of the most violent natural forces the solar system can produce. Its superheated plasma stream moves at extreme speed, carrying radiation and distorted magnetic fields, strong enough to slice through material like a hot knife through soft wax. When a comet gets hit, 3 destructive processes happen almost simultaneously. The plasma slams into the surface with colossal force, dislodging and ejecting the porous material. Radiation and charged particles grab every volatile molecule on the surface, ripping them away in sheets like a storm stripping an earthen wall. An ultra-rapid thermal shock causes ice to expand unevenly, creating propagating cracks throughout the structure. When those 3 mechanisms combine, the outcome is always the same. The comet is torn apart, its surface blown away, and whatever remains becomes an ionized dust cloud. We've seen it dozens of times. Socho has recorded countless moments when comets that merely grazed the sun, vaporized like fireworks hitting water. There have been comets larger and sturdier than ATLAS that were completely blown apart in minutes by a mid-level CME. We call it comet demise, a familiar, highly predictable phenomenon that current models can estimate collapse time with just a few basic parameters. So when an X9 class CME was forecast to slam into ATLAS's region, not a single person in the scientific community considered any outcome other than total disappearance. This wasn't pessimism, it was the plain truth of physics. A comet porous full of voids, made of brittle ice and weakly bound dust, has no chance against plasma hotter than 1,000,000 degrees. One sufficiently large impact instantly ejects surface material, creating tears that destabilize and collapse the entire structure. If it doesn't shatter immediately, it gets peeled layer by layer until nothing remains. I've seen too many examples to believe a comet could withstand a hit like this, and what forced me to reconsider was not just that Atlas didn't disintegrate, it didn't lose even a tiny fraction of material, no ejected dust, no fragments, no remnants of any kind. This is completely opposite to natural comet behavior. When plasma strikes, the surface must explode into fine dust particles that the solar wind sweeps into a long tail. But with Atlas, there was no tail, no dust explosion, no sign the surface had been affected at all. That's what I thought about most. A comet can conceivably survive an extreme plasma event, but surviving without leaving any material loss signal is almost unimaginable. Every comet ever hit by a CME left a very clear death signature: sudden brightness spike followed by collapse, widespread dust, fragmented ionized tail. Atlas had none of those signatures, and when compared to every previous case, from the Kreutz family sun grazers to comets torn apart by CMEs, the difference is stark. Those comets died exactly according to the rules, while Atlas did not. From an engineering viewpoint, this poses a far stranger problem. To avoid breakup, Atlas must have a surface tough enough to withstand thermal shock and plasma impact force. To avoid stripping, its material must be abnormally strongly bound. To avoid having its outer layer ionized away, its composition must have superior radiation resistance. None of that fits a natural comet. Data from Rosetta show comets are thousands of times less durable than concrete. They are brittle, porous, weak, optimized for sublimation, not survival. So why wasn't Atlas destroyed? The simplest hypothesis is that it does not have the porous structure of ordinary comets. This brings us back to the radiation crust. JWST discovered a layer transformed by cosmic rays over billions of years, thick enough to form an unusually hard shell. That layer, if thicker than predicted, could act as natural armor, and if that armor is tougher than we thought, it could be part of the explanation, but only part. Because even with a tough shell, an X9 class CME hit should still change brightness, or at least produce spectral shock. Yet with ATLAS, nothing changed. No loss, no breakup, no trace, no data fitting the familiar natural scenario. So when we say ATLAS should have died, that's not hyperbole. It's the logical conclusion from every prior observation. ETSA's survival isn't just hard to believe, it completely breaks what we thought we knew about comets. And from there, the most important question begins to emerge. If ETSA's doesn't behave like a comet, then what exactly is it? If you followed ETSA's from the beginning of the story up to the point where it irrationally survived an X9 class plasma strike, I want you to pause for a second and focus on the single most important detail that many people have overlooked. ETSA's shell, the thing we call the radiation crust. Because if you're wondering how an interstellar object could pass through a wall of plasma hotter than 1,000,000 degrees without so much as a scorch mark, the answer, or at least the closest thing we have to an answer, lies right there in that shell. Before the solar flare, JWST imaged ETSA's surface and discovered what we initially treated as a sign of aging, a carbonized layer tens of meters thick formed by billions of years of cosmic ray bombardment. At the time, that information was just interesting, a cool footnote in the ETSA's file. But after the CME, when ETSA's returned completely unscathed, as if the plasma had never touched it, the radiation crust suddenly became the most critical piece of the entire story. And if you look at it as an outsider, you'll see it is a literally strange material. The first thing I want you to picture, the radiation crust wasn't formed over thousands or millions of years. It was formed over billions of years. Every cosmic ray particle that hit the surface broke carbon and hydrogen molecules apart, then forced them to recombine into tangled but incredibly tough polymer chains. Repeat that for a length of time our imagination can't fully grasp, and you get a natural composite. Yes, I said composite, with a structure similar to the materials engineers build to protect spacecraft from the hellish heat of atmospheric entry. And here's where it gets interesting. When you place the two side by side, ETSA's radiation crust and the heat shields on modern probes, you start seeing similarities that are hard to call random coincidence. Both rely on stable carbon, both withstand extreme temperatures, both have chaotic but strong molecular networks, and both work on the exact same basic principle: sacrifice the outer layer to protect what's inside. If you're a casual observer, you might think nature probably just made it that way by chance. But if you think like an engineer, you see the bigger issue. The radiation crust doesn't just resemble a heat shield, it functions exactly like one. When the CME swept over, the plasma didn't burn the surface, didn't destabilize the structure. It slid around the shell as if it had met something harder than itself. And most importantly, the energy left no hotspots, no ionized regions. It was dispersed evenly as though ATLS had a gigantic heat dissipation system spread across its entire surface. This is no longer interesting coincidence. This is functional behavior. And when nature displays function this clearly, you are forced to consider the question that sits on the boundary between two fields. Where does nature stop making something that looks designed, and where does design start borrowing from natural laws to perfect itself? I'm not saying ATLS is engineered, but I am saying that if you handed the radiation crust to a materials engineer, they would tell you it has far too many characteristics of an optimized material rather than a random one. Post-CME surface models show this armor has no local weak points. It is seamless, thick, uniform, and lacks the thin patches typical of ordinary comets. That is very hard to achieve if the formation process was merely random accumulation of radiation damage. On the other hand, it also shows no traces of artificial manufacturing, no cuts, no regular patterns, no signs of engineering as humans understand it. The radiation crust stands exactly in the middle of those two worlds, a material that both nature and technology could claim that's my style. And that very ambiguity is what makes ATLS a much bigger problem than simply surviving the CME. Because the radiation crust poses a question no one wants to answer too quickly. Can nature produce a radiation and heat-resistant layer so perfect that it mimics engineering function flawlessly? The answer might be yes, but if the answer is no or not quite, then what does ATLS represent? An interstellar fossil that underwent billions of years of material evolution, an object shaped by nature to a state of optimization that any engineer would have to admire, or a structure created for some purpose and then left to time, which polished its shell until it became perfect armor. All those possibilities make the radiation crust the scariest part of the whole story, not because it is dangerous, but because it forces us to re-examine the boundary between what nature can do and what we thought only technology could achieve. If the radiation armor is the key to explaining why Atlas could withstand an X9 class plasma strike, then the next question anyone following the story has to ask is, what is really underneath that armor, and what gives Atlas the abnormal stability that far exceeds every comet model we've ever built? The core of an object determines everything: strength, reaction to impacts, ability to handle thermal shock, even the activity spectrum. So to understand Atlas, you have to go deep inside it into something no one has seen directly, but everyone is trying to infer from the data that survived the CME. And when you put all the observations together, three major possibilities emerge. Each explains part of Atlas's strange behavior, but none explains everything. They form a logical circle that analysts are forced to keep spinning without being able to settle on a single answer. The first possibility, and the most natural one in the traditional view, is that Atlas has a supercrystallized ice core, a form of matter you can imagine as ice, but no longer brittle, no longer porous, compressed into an almost perfectly stable state. When interstellar material travels for billions of years through deep cold, gets heated and refrozen multiple times, water molecules can rearrange into a far more perfect crystal lattice than ordinary ice in the solar system. If Atlas's core is a block of supercrystallized ice like that, dense, seamless, with almost no microscopic cracks, it would have excellent resistance to thermal shock and pressure, like a gigantic crystal that refuses to collapse. This explains why the CME couldn't transmit energy deep into the core, and why Atlas didn't break the way comets normally do. But this possibility also raises the reverse question: how does an object of cometary origin end up with a nearly perfect crystalline core? That process requires extremely long times and very specific conditions. Not impossible, but so rare it has to be considered an absolute exception. The second possibility takes us into less familiar territory: an undocumented rock metal core. If you look at Atlas's behavior, no dust production, no surface collapse, no brightness disruption, even under intense water loss. Those traits fit better with an object that has a hard, dense core made of tougher stuff than ice. This opens the scenario that Atlas didn't form as a soft comet, but in a stellar system with chemistry radically different from the solar system. Perhaps the material there produced a solid carbon core, altered silicates, or metal compounds never observed in any body near Earth. Such a core would have natural load-bearing strength, like a super tough asteroid, allowing Atlas to survive the CME. But if the core is that heavy and dense, ATLs should show abnormal dynamical signs, tiny orbital wobbles or brightness changes during rotation. Yet observations show it is unbelievably steady, making this dense core hypothesis reasonable but incomplete. The third possibility, and the one most people approach with caution, is that ATLs possesses an internally ordered, engineered-like structure, meaning not necessarily built by technology, but having properties an engineer would call efficient design. Such a core could resemble honeycomb, a uniformly linked lattice, or a layered natural composite. This kind of structure wouldn't need exotic metals or compounds. Just a rational arrangement of matter would be enough to disperse force, disperse heat, and maintain shape under strong impact. That is exactly how aerospace engineering designs heat and impact-resistant materials: light yet rigid cores, uniform order, no concentrated weak points. If ATLs somehow formed a core like that, it would behave almost like an object optimized for survival, even if no one built it. This is not a claim that ATLs is artificial. It merely points out an undeniable truth. ATLS's core behaves in a way natural matter rarely does, yet not entirely beyond nature's capability. You can call it natural structure if you want, but when an object acts like design without bearing design marks, you have to ask, did nature do this randomly, or was ATLs formed in an environment that forced matter to follow order? All three possibilities, supercrystallized ice, special rock metal core, or engineered like ordered structure, have supporting data. None are wrong, none are sufficient to conclude. ATL sits right in the middle of the three, like a blur that both fits and doesn't fit each hypothesis. And it is precisely that close but not quite quality that keeps the question, what exactly is ATLs, wide open. Not because of missing data, but because the data is too good, too consistent, and too hard to slot into any familiar category. Occasionally, science encounters objects that refuse to stay inside any definitional box. ATLs is one such case, a core tough enough to defy plasma, strange enough to defy models, and silent enough to reveal nothing beyond the effects it forces us to observe. And at this point, the most honest thing the storyteller can say to you is, ATLS's core is the question, not the answer. When Atlas's core became a bigger question mark than any model could fully explain, the scientific community, which had seemed united in the early stages, began splitting into two distinct camps. And if you're following the story, you'll see that so very split says more about how unusual Atlas is than any physical datum. One camp, call it the purely natural camp, believes everything we're seeing can be explained by extreme variants of known natural processes: supercrystallized ice, tens of meters deep carbonized crust, a core formed in an environment completely unlike the solar system, and lots of random combinations producing a strange but still natural object. This camp argues that in a universe of hundreds of billions of galaxies, absurdly rare cases not only can happen, they must happen. To them, Atlas is a pricey fascinating outlier, but still belongs to nature. And they have a point. Diversity is the universe's biggest law. But the other camp, the anomaly-driven camp, if we name it accurately, sees Atlas differently. They register not just one anomaly, but a stack of anomalies layered in a way that feels uncomfortable for a simple natural explanation. They point to the abnormally flat orbit, the absurdly stable speed, the brightness doubling the standard model with no dust tail, the crust functioning like a heat shield, the unbelievably stable core, and most critically, surviving an X9 class CME without a scratch. To this camp, Atlas isn't necessarily non-natural, but it certainly isn't a normal comet, isn't easily classifiable, and may belong to a category of objects we haven't named yet. And here's the real flashpoint. The difference between the two camps isn't in the data. The data is the same, but in interpretation, in how much abnormality each side is willing to accept, and in how strongly each believes nature can produce irregularities that look like design. But one factor has made this divide sharper: data transparency. Because right after Atlas survived the CME, major institutions started becoming cautious about releasing raw data. This isn't conspiracy. The scientific system is naturally careful with sensitive or unprocessed data, but that delay created a vacuum just when people needed answers most. And when there's a vacuum, suspicion slips in. Some scientists want the data released immediately. No delays, no filtering. They believe the more people analyzing it, the faster the solution. This side stresses that Atlas cannot be fully explained by standard models, so the data must be open to the entire young national community. They argue this isn't just a rare phenomenon, it's a once-in-a-lifetime chance to understand interstellar material at an unprecedented level. On the opposite side, the cautious camp says rushing the data out will lead to misinterpretation, hype, or non-scientific hypotheses before rigorous analysis is complete. They point out that even the simple data from Umuwan got distorted by the media, so a complex event like Atlas needs thorough vetting before release. To them, caution is necessary to protect scientific integrity and avoid scenarios where the public misunderstands how weird Atlas really is. Yet that very caution has pushed debates in another direction. Is the delay because the data contains something too hard to explain? Is part of it stuck at needs re-verification or showing distortions the models can't handle? Those questions don't come from conspiracy theories. They come from the scientific community facing a phenomenon outside its comfort zone. One side trusts nature, the other sees too many warning signs, and between them sits the data both sides look at, but each sees a different story. And if you follow this debate, you'll notice one important thing. The split itself isn't bad. It reflects the truth that Atlas is forcing us to widen our explanatory range. One side is trying to keep the old launchpad of knowledge, the other is trying to push the frontier, and both are needed to avoid sliding into extremes. But the most striking thing is how their attitudes reflect a shared anxiety. Nobody fully believes the current models are enough to cover Atlas. One side thinks nature is more complex than we realize. The other thinks Atlas is a signal of something beyond the comet category. And you, the one watching, will see it clearly. If one interstellar object can split the scientific world this hard, then the split itself is proof that Atlas is no ordinary event. This is no longer a debate about an ancient ice dust chunk. This is a debate about the boundaries of understanding. When the scientific community split over Atlas's nature, a deeper question began surfacing from the very data they were arguing about. If Atlas isn't entirely comet-like, then which of the big scenarios modern astrophysics has proposed does it fit into, including the controversial and fascinating hypothesis that objects like Atlas could be planetary seeds, or even a form of interstellar probe capable of enduring cosmic time and violence? To understand why that question isn't as far-fetched as it sounds, you need to grasp the planetary seeds model, an idea once considered too bold, but lately backed by more data than ever. According to this model, not all planets are built from tiny dust grains sticking together as textbooks describe. Instead, some planets may start from interstellar objects a few hundred meters to a few kilometers across, drifting through the galaxy. When such an object enters the gas dust disk around a young star, it connects as a nucleus that attracts matter, creating gravitational compression zones and triggering much faster accretion than the classical model, a planetary seed sown into a new stellar system. From this perspective, ATLS could be a leftover fragment from planet formation in a stellar system that vanished billions of years ago. Its long survival and thick radiation shell fit the idea that ATLS has been wandering the interstellar medium long enough to become an ultra-stable object capable of withstanding impacts, radiation, and extreme temperature swings. If you view ATLS as a planetary seed, its behavior during the CME stops looking irrational. A planetary seed has to be able to survive major shocks because planet formation is one of the harshest environments in the universe. Collisions, extreme heat, intense UV radiation, and constant impacts with other bodies. But ATLS exceeds even the expected durability of a normal planetary seed, and that's where the second possibility appears, the one that forces everyone to choose their words very carefully. Could ATLS be some form of interstellar probe? I'm not talking about shiny metal spacecraft straight out of science fiction movies. If an ancient interstellar probe exists in the galaxy, it wouldn't look like the spacecraft humans imagine. It would look like rock, like ice, like a natural piece of space, because that is the most effective way to stay hidden in a merciless environment for billions of years. A real probe, if it exists, wouldn't be fragile, wouldn't need continuous propulsion, wouldn't require active power systems. It would be completely passive for most of its journey, only waking up or reacting when it encounters the right environmental conditions. And most crucially, it would have to withstand interstellar radiation for billions of years. It would have to resist cosmic dust impacts across millions of generations. It would have to survive passage through the heliospheres of many different stars. It would have to endure extreme events like X9 class CMEs, just as ATLS did. Technically, if you asked a team of engineers to design an object meant to last billions of years in the unforgiving cosmic environment, they would come up with something very similar to ATLAs, an ultra-tough carbonized outer shell for radiation protection, a stable, seamless core with excellent force dispersion, an internal structure with minimal weak points, and the ability to retain shape under plasma, extreme heat, or electromagnetic shock. Nothing about ATLAs clearly screams probe, but many details: the abnormally flat orbit, strangely stable brightness, complete lack of dust, CME endurance, radiation armor that works like a heat shield, a harder ordered core, when placed side by side, make this possibility impossible to dismiss. And to be fair, both major possibilities, planetary seed and probe, have strengths and weaknesses. Planetary seed explains age, thick crust, the billions-year journey, and structural stability, but it struggles to explain the lack of dust, lack of weakening, and zero wear after the CME. Probe perfectly explains the bizarre resilience and aligns with the fact that ATLAs behaves too much like an optimized object, but probe lacks direct evidence, and science can't conclude based solely on the feeling that it looks designed. The most important thing I want you to understand is that both possibilities remain wide open, because ATLA sits exactly on the boundary between them. It is tough like a design, yet ancient like a fossil. It is stable like an engineered object, yet carries natural cosmic ray traces. It behaves like an object with purpose, yet could just as easily be the product of billions of years of material evolution in deep cold space. And that very overlap is what shifts the question about ATLAs away from where did it come from and toward what was it made to do, regardless of whether that purpose belongs to nature or to some ancient civilization. If ATLAs is a planetary seed, it is a clue to how nature builds worlds. If ATLAs is a passive probe, it is a clue to how intelligence survives across cosmic time. But until the data is enough to rule one direction out, ATLAs remain standing at that exact intersection, a place no previous interstellar object has ever reached. When I look at the 7-12 billion year figure in ATLAs' file, the first thing I think isn't, wow, it's ancient, but this makes no sense under any physical standard we currently use to describe comets. I want you to try to picture this with me for a second. We're talking about a small object a few kilometers across with no protective shield, no magnetosphere, no atmosphere to retain heat, no obvious self-repair mechanism. Yet it has outlived the sun, outlived most stars in the galaxy, and possibly outlived the very astronomical structures we rely on to describe cosmic history. That's not just weird. It breaks the intuition of you, me, and anyone who has ever designed something to survive a harsh environment. Because if you've ever built anything meant to last, one rule: material always loses to time, always, no exceptions. But ATLS doesn't. We are standing in front of a small object that time, the greatest enemy of every structure, seems to have refused to touch. So the biggest question here isn't where did ATLS come from, but why hasn't it been destroyed yet? To answer that, we have to look at the three greatest threats of cosmic time that any engineer would immediately recognize. First, collisions. Think of ATLS as a pebble thrown into a storm-tossed ocean, except this ocean lasts billions of years and the storm never stops. Over that span, ATLS gets bombarded by interstellar dust, micrometeoroids, and debris from supernovae thousands of light years away. Every tiny impact chips away at the structure, and if you've ever seen images of comets after collisions, you know exactly what should happen. Fragments fly off, cracks form, and eventually it breaks into smaller chunks and disappears. But ATLS doesn't. It shows no erosion, no fractures, no tearing. It has survived as if billions of years of impacts were nothing more than gentle taps on a surface too hard to care. Second, radiation. We know high-energy cosmic rays act like an invisible army that dismantles matter molecule by molecule. An unprotected small body would slowly disintegrate into fine dust. But you and I both know ATLS didn't follow that script. Radiation didn't destroy it. It forged it. The radiation crust ATLS carries isn't some random natural skin. It's like a carbon composite layer gradually built up and optimized over billions of years. The way nature turned destruction into reinforcement, I'll be honest, is extremely close to the logic of design. You don't have to call it engineering, but if you've ever optimized materials, you'll instantly see the implication. ATLS got stronger, tougher, more stable over time. That is wildly abnormal for a comet and eerily familiar to technology. And finally, Thermal shock. This kills structures faster than almost anything else. An object swinging from near absolute 0 to million-degree environments in hours or minutes will expand and contract nonstop. The result: cracks, fractures, collapse. No brittle material survives that long term. Yet ATLS has for billions of years. It has passed through the heliospheres of countless other stars, slammed into hot stellar winds, frozen solid, then heated again, and never cracked. If you've ever designed materials, you know this is practically impossible without an extraordinarily stable core structure. These three threats, collisions, radiation, thermal shock, are each enough to kill a comet in a few 100 million years, never mind billions. Yet ATLS beat them all. So what does that tell us? That ATLS does not operate the way comets operate. That ATLS has survival capability far beyond what nature normally grants objects like it. That ATLS is either an extremely rare structure or the product of a primordial environment we don't yet understand, or formed in an era when physical conditions allowed small bodies to become super durable. You and I both know we can't conclude anything while the data is still incomplete, but we also can't ignore the fact that no small object, even solid asteroids, has a 12 billion year survival record without severe deformation. And if ATLS has lived that long, the scary part isn't that it survived the CME. The scary part is that it survived everything that came before it. If we want to understand ATLS, we shouldn't ask, how is it still here today? We should ask, what exactly did it survive over 12 billion years? Just when we were still trying to figure out how ATLS could survive the X9 class CME completely unscathed, the period afterward opened up a whole new series of anomalies. And I'll be straight with you, what ATLS showed after the CME is even harder to explain than its survival itself. The first thing you and I both see clearly in the data, ATLS's brightness began changing in a way that looks nothing like a comet. Instead of dimming from mass loss or spiking and then crashing like typical post-shock behavior, ATLS brightened in steps, held steady, then brightened again, as if it had an internal feedback mechanism, a kind of self-regulation that natural objects rarely have. Brightness no longer matched distance from the sun, no longer depended on solar wind, no longer followed outgassing rhythm. It increased according to its own rules. If you ask me what that feels like, I'll say it feels like a threshold-based system rather than simple material sublimation. Then came surface temperature, the point that made many people reopen the data 3 or 4 times to check for measurement error. An object hit by million-degree plasma should show rapid cooling in the days afterward. Basic physics. But ATLAS didn't. Its pre- and post-CME temperature was virtually unchanged. No rise, no fall, no natural response. That leaves one of two possibilities. Either ATLAS's radiation crust is so efficient it completely blocks heat transfer in and out of the surface, or the CME simply couldn't thermally affect ATLAS's structure the way we think. Either way, this is not standard comet behavior. And then we get to the third anomaly, possibly the strangest, ATLAS's plasma tail. This wasn't an ion tail, wasn't a dust tail, and definitely wasn't a chaotic plasma tail stretched by the solar wind. ATLAS's post-CME tail was thin, narrow, unbelievably stable, and most importantly, it did not fluctuate with the solar wind. It held its shape no matter how ATLAS moved through the magnetic field. It didn't diffuse with distance. It appeared as a shaped plasma ribbon, reminiscent of what engineers call field shaping. But let me be clear, we have no data to conclude this is a system, yet its behavior is not natural looking. When you line up these three phenomena, step brightness, constant temperature, and a shaped plasma tail, you see a common thread that I believe any engineer or analyst spots immediately: stability, not chaos, not passive reaction, but synchronized stability. This is not what comets show after being hit by an X9 class flare. This is what you expect from a structure capable of dispersing energy, maintaining surface conditions, and responding like a system. I'm not saying ATLAS is a technological system, but I am saying its post-CME behavior is far more organized than any recorded comet. And that's the truly frightening part. The CME didn't just fail to destroy ATLAS, it seems to have triggered a new operational state in the object. So the question now is no longer why did ATLAS survive, but what is ATLAS going to do next? Just when the post-CME anomalies still hadn't been explained, another reality started pressing down on us, harder than anything before. The ATLAS observation window is closing, and not slowly or gently. It's slamming shut fast, clean, merciless, like automatic lab door sealing when the experiment time is up. ATLAS, after surviving an X9 class CME, as if it was born to face stellar over-energy outbursts, is now leaving the sun at a speed that allows no complacency. You and I both understand the principle. Light is the only thing that lets us observe an object hundreds of millions of kilometers away. And once ATLAS slips into the dark zone where sunlight is too weak to reflect back, it will vanish from all human monitoring systems. No satellite can chase it. No telescope can catch it. No second viewing session. No one more time. We have only a few weeks Yes, the final few weeks to collect any usable data before ATLAS becomes an anonymous dot in interstellar darkness. And the situation is even tenser because ATLAS, instead of settling down after the CME like any normal comet, keeps changing in ways no one predicted. For example, its already anomalous brightness has now shifted to small but distinct step oscillations, as if an internal algorithm is deciding outgassing levels instead of ordinary thermal physics. Brightness no longer follows any heat, orbit, illumination model. It rises on its own schedule, unrelated to any environmental variable. ATLAS is brightening as if it is responding rather than reacting. This has forced many research groups to push light curve modeling to detail levels never used for comets. And then there's something even more absurd. ATLAS's surface temperature is almost perfectly constant. This makes anyone who has worked with material analysis frown. An object hit by million-degree plasma should heat up and then cool rapidly, but ATLAS shows no change. Pre- and post-CME temperatures are the same, to the point that most teams suspected sensor error. Unfortunately or terrifyingly, data from 3 different instruments all confirm it. ATLAS is maintaining its temperature as if it has an internal stabilization mechanism. That is not in the Comet behavior catalog. It's what you expect from a structure optimized not to absorb environmental heat. But the anomaly sparking the most debate is the plasma tail, the one that appeared after the CME yet doesn't act like a normal comet ion tail. Atlas's plasma tail does not wiggle with solar wind, does not stretch or twist with magnetic field variations. Instead, it stays stable, narrow, sharp-edged, like a plasma thread shaped by the object itself. It doesn't fade with distance. It isn't affected by direction of motion. It doesn't deform as ATLS rotates relative to the sun. If you ask me what this reminds me of, it looks like field shaping, a form of plasma shaping that only happens with stable internal electromagnetic properties. Nature can do that, but no comet has ever shown anything similar. And when 3 anomalies, non-cyclic brightness, locked temperature, shaped plasma tail appear together right after an extreme event, they stop being 3 separate events. They become a signal chain, a chain with logic, a chain consistent enough that any engineer recognizes this is not random chaos. This is a state. And what makes everything 10 times more urgent is that ATLS is changing every day, and we don't know whether it is settling back down or shifting into an entirely new behavior. Research teams are wringing every instrument dry. JWST is pushing infrared spectra to the limit. Hubble is extending exposure times to the point of noise risk. Ground stations are running orbital and plasma models 24/7. Everyone understands if ATLS changes one more time, that could be the last change humans ever see. And if it stays the same, we still have only weeks to record this strange state before it disappears from our view forever. I want you to feel this clearly. This is not just the final phase of an observation campaign. This is the moment we are forced to face the fact that ATLS, an interstellar object older than the sun, tougher than any known comet, and stranger than current models allow, is about to leave our system forever. No return, no trace. And if we miss this window, every answer goes with it into interstellar darkness. We have only weeks. That's it. The window is closing, and there's no way to open it a second time. Just as the ATLS observation window is closing and all of us can feel the pressure of time, there is one final question I believe none of us can dodge anymore. What is the true meaning of ATLS surviving, not just technically or physically, but in terms of how we understand the universe and our place in it? Because if you lay out every anomaly of Atlas on one plane, from the abnormally flat orbit, stable speed, nonlinear brightness, total lack of dust, radiation crust thick as armor, constant temperature maintenance, post-CME shaped plasma tail, to absolute survival after an X9 class solar flare, without losing even a tiny piece of structure, you realize this is no longer the story of a weird comet. This is an entire layered system of anomalies, unified, non-contradictory, and most terrifying of all, consistent over time. One anomaly can be called coincidence. Multiple anomalies can be blamed on statistical extremes, but a long, continuous, synchronized chain of anomalies with internal logic, that is not the chaos of nature. It is the sign of the only 2 final possibilities science is forced to accept, however uncomfortable. The first possibility, ATLAS is a natural object, but belongs to an extremely rare form of matter that barely exists in the present universe. A fossil from the primordial cosmos, when physical conditions were completely different from now, when radiation was stronger, matter density higher, and molecular processes violent enough to create structures we cannot reproduce in labs. If ATLAS belongs to this group, it is a fragment of the primordial era, a form of matter that survived generations of stars, multiple supernovae, countless plasma environments, and it represents the physical memory of a young universe. Meaning ATLAS is not mysterious, it is history. It is evidence of conditions we have never witnessed, but that existed before Earth, the Sun, or any planet in our system formed. But the second possibility, the only one left once we strip away every assumption, is that ATLAS is not entirely natural in the passive sense. not a shiny spacecraft, not a device with antennas or reflective metal, but an object built under the philosophy of survive as long as possible, a passive probe that some civilization in galactic history might have sent out and left to drift among the stars for billions of years, an object built not to transmit, not to observe, but simply to endure, to remain intact, to resist destruction, to become a wordless message. If someone finds me, you will understand something about the civilization that made me, or about this universe itself. And the thing is, if you ask one team of engineers to design something that could survive billions of years of interstellar radiation, millions of microimpacts, continuous thermal shock, and finally an X9 class solar flare, they wouldn't design a metal ship. They would design something very much like Atlas, a stable core, an ultra tough carbonized armor shell, low thermal conductivity, plasma dispersion capability, and near absolute thermal behavior stability. I'm not saying Atlas is artificial, but I also can't ignore the overlap between what optimized engineering demands and what Atlas demonstrates. And that is why this final part is not meant to give a conclusion, but to hand the question back to you, the person watching, the person who knows the universe is never as simple as we want it to be, because after all the data, after every graph, after every broken model, and every shattered anomaly chain, the final question still rings out loud, clear, and perfectly in the spirit of an American audience that isn't afraid of big questions. If an object can survive an X9 class solar flare without weakening at all, what exactly is it trying to tell us about the universe or about itself? If you want to keep following the journey to decode Atlas and the mysteries unfolding before us, subscribe now so you don't miss any future parts. And if you believe stories like this deserve to be told more, hit subscribe so we can go together all the way to the edge of the universe.